So on number 43 from section 4.1, we are asked to find the critical points. And not only that, determine absolute max and min. But the derivative on this one is sad. It's like crazy. So here we go. Y equals 2x to the x. And just as a thought, we know how to take the derivative of a constant to x. The derivative of that is I am my own grandpa, ln b. And we know how to take the derivative of a variable to a constant, that's power rule, n x to the n minus 1. But we have a variable there and a variable there, confusion. I don't know how to do that. So the secret we learned is you take the ln of both sides. Why would we take the ln of both sides? Because we have the rule where you can p in front of a log. So ln of y equals x ln of 2x. This is not x, so it's a box. The derivative of left side, y is our function, so that's a box. ln of box is 1 over box times the derivative of box. Whoa, that's not the derivative of box. I got distracted. This side we have a product rule, two things being multiplied. You leave the first alone, take the derivative of the second. The derivative ln of box is 1 over box times the derivative of box. Ooh, that's nice, that's just 1. Plus, and then you take the derivative of the first and you leave the second alone. So we get 1 over y dy dx is 1 plus ln of 2x. But we're trying to find dy dx. To get rid of the y, we multiply both sides by y. So we finally get dy dx. And for those of you who are freaking out, I don't remember seeing a problem like this on the AP test, but this is good practice, good skills to have. What is y? I'm going to replace y with what it is, 2x to the x. All right. Now, we set both these equal to 0 because we want to find the critical points. 1 plus ln of 2x equals 0, and 2x to the x equals 0. Well, I'll say this much. You can graph this on your graphing calculator, and you will see it never crosses the x-axis, I believe. I'll double check that. I believe that has no solution. No solution. It never equals 0. Okay? What are we doing, 43? I can double check that for you so I don't mess up on this one. 43. Yeah. So I believe we're okay with that. So how do you solve this? How do you solve this? Algebra, subtract 1 from both sides. You e both sides to get rid of the ln. You have to know those are inverse functions, which makes this 1 over e. Divide both sides by 2. So x equals 1 over 2e. That is our critical point. Back to the original problem. I will copy all this. Back to the original. Oh, don't, oh well, I cut it. At least it wasn't the cheese. Okay, so you should know max and mins occur only at critical points or endpoints. So therefore, it can only occur at point 1 or at our critical point, 1 over 2e, or at endpoint 1. Now, if you plug this into the original function, I will tell you the values you get. At point 1, you're going to get 0.851. At 1 over 2e, it's approximately, I already have the approximate, 0.832. And at 1, it's just 2. So what is the maximum value? Clearly, there's the max. What's the minimum value? That is the minimum value. And you can graph this and verify it, but we are running out of time, so I will not do that. Maybe I will. We have time. We can do this. Yeah, we can do this. We can do this. Let me graph this. We almost have it already. It's almost done for us. Just get rid of that and make it 2x here. Look at that in a parenthesis. And our domain is 0.1 x to 1. That's it. And you can see we had one critical point. It's right there. That's the smallest point on the graph because the slope of the tangent line is 0. That's the 1 over 2e we found. The maximum is at the right end point of 2, like we found. So there you go. That is the graph. That's what's happening.